Alright, so I'm going to start my lecture for chapter 24. I'm only going to do the first half of the chapter because that's what we covered today during streaming. I apologize for Twitch not working as well as we had hoped, but I still think it was okay, and I think you guys got most of the material, but me being me, I forgot to hit the record button, so here I am recording again. So I'm just going to cover what we covered earlier today while streaming, and then we'll finish the chapter on Thursday, and then we'll see where we're at. Alright, so chapter 24 is all about nuclear chemistry, a topic I enjoy since this is what I did in grad school. I used a nuclear reactor at UC Irvine, and that was fun. Anyways, just to get started, just to compare what we've been talking about so far with chemical reactions versus nuclear reactions. With chemical reactions, you can start a fire. With nuclear reactions, you can flatten a city. Huge difference in amounts of energy involved here. Because with chemical reactions, you're just talking about breaking bonds, forming bonds. It's just the electrons that are involved. But with nuclear reactions, the nucleus is involved. The nucleus is making a change, and there's huge amounts of energy involved with making a change in the nucleus. Now it says here on my little graphic that about 11% of the worldwide energy use comes from nuclear energy, meaning we use nuclear power to generate electricity. Well, you're going to see that number going down in the future because nuclear reactors are getting old and they're expensive to maintain, and they're going to start shutting down. So I don't know how much longer these guys are going to be around. And if you want to make a new one, it takes several years just to build one. So anyways, but they're still used in research. And I know that at UC Irvine, where I used to be a grad student, they're still using the nuclear reactor over there, and they're still using it for research. So this is still a current thing that we do. Alrighty then, onward. So we need to remind ourselves back from chapter 2 how we represent an element with the complete chemical symbol. We have the symbol of the element. Let me bring up my little highlighter thing here. How about let's try the laser pointer. Alright, so here's your chemical symbol with the C. Here my example is carbon 12. So I've got a capital C for carbon. The number on the lower left is the atomic number, which is the number of protons. On the upper left is the mass number, which is equal to protons plus neutrons. So with carbon 12 has 6 protons and 6 neutrons for a mass number of 12. So this should be review. You should have seen this before. I'm just refreshing your memory here. Alright. Now we do have a thing called isotopes, which you also should have seen from chapter 2, where all atoms of the same element have the same number of protons. So every carbon atom will have 6 protons. But they can have different number of neutrons, and these are called isotopes. And here I have up here an example of 3 isotopes of uranium: uranium-234, 235, and 238. These are your 3 naturally occurring isotopes of uranium that occur naturally in the soil. It's very difficult to separate out the isotopes. It's generally done using centrifuges. And if you hear about various countries building a lot of centrifuges, people start getting upset because they want to know, okay, what are you using them for? Because obviously the only reason you're buying all these centrifuges is to isolate uranium-235. What are you going to do with it? And everyone gets upset. So that's what that's all about. In any case, when we want to talk about a specific isotope or a specific what we would call nuclide in a nuclear reaction, we give the name of the element followed by the mass number. So all my 3 uraniums up here, they all have 92 protons, but they have different number of neutrons. So they have different mass numbers. Alright, onward we go. When we show nuclear reactions, there are some subatomic particles that are going to show up in these nuclear equations. The electron we represent with an E, and then an upper left 0 and lower left -1. This is for accounting purposes. It's not like it's a negative proton or something. It's just, again, the -1 is for accounting purposes. Here's our proton right here. We give it a P with a 1 and a 1 because the 1 proton has atomic number 1 and a mass number 1. And then for the neutron, we have an N, lower left 0 because there's no protons present, mass number of 1 because we do have a neutron here. Alright, so here's your electron, here's your proton, here's your neutron. These are going to show up in your nuclear equations. Alright. Now, there's a fair number of nuclides, meaning isotopes with a specific number of protons and neutrons, that are unstable, which means we have observed them to transform over time into a different element. These are called radionuclides. They're radioactive when they give off radiation, and they start out one element and they turn into a different element when they're done. And there's several different ways a nuclide can decay into something new, making a new element. And we use nuclear equations to show how this happens. So remember, in chemical equations, the number of atoms of each type of element need to appear on either side of the arrow. You need mass balance, and you need a charge balance. In a nuclear equation, we still want mass balance, but we're doing it in a different way. Keeping track of atomic numbers and mass numbers. Your atomic numbers and mass numbers need to balance. This is how we keep track of mass balance in a nuclear equation. So here's our main types of radioactive decay we're going to talk about. Alpha bit decay, beta decay, gamma emissions, positron emissions, and electron capture. Okay, an alpha particle is the helium nucleus. It has no electrons. An alpha particle is 2 protons and 2 neutrons, which is the nucleus of a helium atom. And so there's 2 ways you can show this in a nuclear equation. You can show it as helium with the 4 and the 2, or you can show it as an alpha with a 4 and a 2. Either one are fine. Now you notice in this example, I've got uranium-238. He's going to decay, give off an alpha particle, and the uranium nucleus will turn into thorium. And watch what's going on with these atomic numbers. Total of 92 on the left, 90 plus 92, 90 plus 2 for 92 on the right. So everything on the lower row has to add up. 92 here, 92 here. That's how we keep track of mass balance. And then on the upper row, we have a total of 238 on the left, 234 plus 4 for 238 on the right. So this is how we go about mass balance with a nuclear equation. All your atomic numbers need to agree on left and right side of the arrow, and the mass numbers need to equal each other on either side of the arrow. Total of 28 here, total of 28 over here. Alright, let's go on to our next form of decay. A beta particle is an electron. And like I mentioned before, we represent it with a 0 on the upper left and a -1 on the lower left. You can give it a little Greek symbol beta if you like. This is also fine. But more common, you'll just see the E. So in this example, we have iodine-131. He's going to undergo beta decay and turn into xenon and give off an electron. And this is how I represent an electron. Look at the mass numbers. 131 total on the left, 131 total on the right. And the atomic numbers, 53 on the left, 54 minus 1 is 53 on the right. Again, this is how we do mass balance. Now you're seeing, okay, this is why that -1 is there, because my atomic number went up by 1 when I underwent beta decay. Okay, so there's that. All right, next we're going to do gamma emission. Gamma emission is when a gamma ray is emitted during a nuclear reaction. You generally don't get gamma rays all by themselves. They generally accompany another particle, like an alpha particle or what have you. A gamma ray is part of the electromagnetic spectrum. It has no mass, it has no charge, hence the zeros. Okay. Why are we not going down? There we go. So here's a summary of these 3 main forms of radioactive decay: alpha decay, beta decay, and gamma decay. Remember, these alpha particles are just the nucleus of a helium, so they don't have any electrons and they have a +2 charge. Electron has a -1 charge, and gamma has no charge. Alpha particles are much more massive than electrons. Gamma has no mass. Alpha particles have very difficulty in penetrating anything because they are so heavy and they have that charge on them, so that means it's really easy to stop these guys you can stop an alpha particle with a couple centimeters of air. This is what he looks like, helium nucleus. An alpha particle is not nearly as massive as alpha. It is more penetrating depending on how energetic your electron is, and they do have a range of energies depending on who's emitting it. Gamma ray, very penetrating. It's a high energy photon, and these are the guys that are used in nuclear medicine because they are very penetrating, so they can pass through your body and give the doctors an image of your insides without cutting you open. So very useful tool. Alright, so next type of decay is positron emission. A positron is an anti-electron. It is antimatter. And what happens with antimatter, when antimatter and matter collide, they annihilate each other and turn into pure energy. Of a very specific energy. In any case, so that's what positrons are, and positron is the P in PET scans. Okay, so it is very useful in nuclear medicine also. They're quite penetrating. So when we say a positron is an anti-electron, it has the same mass, but the opposite charge. So a positron has a positive charge, but is only as massive as an electron. It is not as massive as a proton. It is not the same thing as a proton. If a proton and electron come together, you've got hydrogen. If a positron and electron come together, they're going to annihilate each other and turn into energy, because positron is antimatter. Okay? In any case, with our positron emission, you'll see we have a total of 6 for the atomic number on the left. 5 plus 1 is 6 on the right. Mass number 11 on the left. Mass number 11 on the right. We still have mass balance going on, but we do have different elements on either side of our arrow. That's going to be your typical nuclear equation. One element turns into another. Electron capture. This does not happen as often. Actually kind of cool, because what happens is the nucleus actually grabs an electron that's part of the electron cloud, grabs it, takes it into the nucleus, and now you've got a new element. So here, rubidium-81 grabs an electron from its own cloud, turns into krypton. Kind of cool. Anyway, watch your mass numbers and atomic numbers. 37 minus 1 is 36. Mass number doesn't change. Alright, so now we're going to work some problems. Here's 24.1 in the book. So what we want to do is write some nuclear equations. First we'll do thorium-232 undergoing alpha decay, and then we're going to do zirconium-86 undergoing electron capture. So first thing we need to do is find thorium on the periodic table and find the atomic number, because we won't know the atomic number of the product until we know the atomic number of the reactant, right? So thorium has an atomic number of 90, so we have this. So this is how we get started. Okay, I've got the mass number, it was given to me in the problem. Got the atomic number from the periodic table. Now we're told it undergoes alpha decay, so one of the products is an alpha particle. So we can go ahead and put that in our equation too, and then we'll have to figure out what the other product is. So there we go. Now we've got that. So keeping in mind our mass balance rules, the other product has to have an atomic number of 90 minus 2. And the mass number of the other product should be 232 minus 4. So our final nuclear equation is this. Radium-228. So when I figured out that this guy has to be 88, because 88 plus 2 is 90, I've got to go to the periodic table. 88 is radium. Okay, moving on. Here's letter B. Zirconium-86 undergoes electron capture. Go to the periodic table, find the atomic number for zirconium. It's 40. So, it undergoes electron capture, so we know an electron has to also appear on the left side of our arrow. So here we go. Now we got to figure out the product. So the atomic numbers on the right has to be equal to what's on the left. So 40 minus 1 is 39. And we know the mass number won't be changing. So now I've got yttrium-86 instead of zirconium-86 for my product. Alright, so here's a summary of various particles we've been talking about. Here's our neutron, here's our proton, here's our electron, alpha particle, beta particle, positron. Remember, a positron and a proton are not the same thing, even though they're both positively charged. Proton is much more massive. All right, onward we go. Here's some sources of nuclear particles. A source of beta particles is iodine-131, for example. There's actually a lot of sources of beta particles, not just that. This is just an example. Sources of positrons. You can kind of think of a proton turning into a neutron and a positron. It's kind of not really what it is, but it's kind of an oversimplification, but it'll work. With electron capture, a proton will grab the electron and turn into a neutron. Again, it's kind of an oversimplification, but it's an easier way to think about it. All right. Now, why is it that some of these nuclides are more stable than others? Anytime you have more than one proton together in the nucleus, these protons are going to repel each other because they have the same charge. So we have something that's called the strong nuclear force to keep the nucleus from flying apart, holds it together. And a big part of this is the neutrons. You can think of the neutrons as the glue to hold the protons together. Ugh, I just got an email. That's okay, can wait. Now what's important to stability is your ratio of neutrons to protons. If you have a small nucleus, 20 or smaller, a stable nuclei will have a ratio of 1:1 for your neutron to proton. When you get bigger than 20, you need more glue, meaning more neutrons to hold everything together. So when you get over here to these bigger elements with bigger nuclei, your ratio needs to get closer to 1.5 to 1. We do have some magic numbers, but we're really not sure why. If you have these numbers of protons or neutrons, you tend to have a stable nucleus. Nuclei with an even number of protons and neutrons tend to be more stable than with odd numbers. We really don't know why. This is just an observation. Kind of cool though. Alright, why are we not going down? There we go. So what we want to do is compare nucleus to this belt of stability that we have here in orange. If we're above the belt, we have too many neutrons. We're going to undergo beta decay. If we're below the belt, we have too many protons. So we're going to decay by either positron emission or electron capture. Now we're going to work a problem 24.2 out of the book. Oh, but first we have to talk about this. Alpha emission. Sorry. There are no stable nuclei with an atomic number greater than 83. They're all unstable and they all undergo alpha decay. Alright, so here's 24.2, predicting nuclear stability. So what you've got to do here is look at your ratio of neutrons to protons. So is neon 18 stable? No, it doesn't have enough neutrons. Its neutron to proton ratio is only 0.8. We need more neutrons to get it stable. Sulfur 32 is stable because he has a 1:1 ratio of neutrons to protons. Thorium is radioactive simply because it's big. Atomic number 90. He's going to be unstable just because he's too big. And barium-123 is radioactive because he doesn't have enough neutrons. He's a large nucleus, so his ratio of neutrons to protons needs to be closer to 1.5, and his is only 1.2. Not enough neutrons to be stable, not enough glue in the nucleus. Alright. Now a lot of times when a element goes under radioactive decay, sometimes its daughter product is also radioactive. And here's a really good example where we start with uranium, and he goes down to thorium, then radium, then radon. Radon's a gas. Uranium occurs naturally in the soil. So if you've got radon gas in your home because your house is built on soil with uranium, now you've got a problem. Because radon will decay into polonium, which is a solid. And so if you breathe this stuff in and it decays in your lungs, now you've got polonium solids in your lungs, and now you've got something that can cause cancer. And now you've got a problem. But typically with your radioactive decay chain, you're going to end up with lead. Lead has about 1 gabillion stable isotopes, and that's generally your endpoint for any radioactive decay chain. Okay, not 1 gabillion, maybe half a dozen. Alright. So we've been talking about things that are radioactive. They give off particles, they undergo decay. How are we going to measure all this stuff? Well, there's a lot of different units we use. This is just to get us started. What we want to do is measure the activity. What is the rate where a sample decays? What's the rate where one nucleus turns into another? There's various ways we can talk about that. The first one is specific activity, decay rate per gram of stuff. There's the Becquerel, which is defined as 1 disintegration per second. Becquerel is named after the scientist who discovered radioactivity. Then, of course, there's the Curie, named after the Curies. That's defined as 3.7 times 10 to the 10 disintegrations per second. Now, that's a lot of disintegrations per second, so when we generally talk about radioactivity, or activity in general, we're usually talk in terms of millicuries or microcuries in the real world. All right. Onward. So your activity is directly proportional to the number of nuclides present that are going to decay. And so we have this proportionality constant here that we call the decay constant. This is going to look familiar to your kinetics chapter. Your change in number over time is proportional to the number. But remember, we're talking radioactivity now. This is not concentration. This is number of nuclides, number of nuclei that are present. And then here's our decay constant. Okay, so we're going to work a problem 24.4 in the book about relating decay and activity to the number that's present. All right, so here's our problem. We have a sample of antimony 122. And it's going to emit 2.76 times 10 to the 8 beta particles per minute. What is my specific activity of the sample? Meaning I need to convert all this information into curies per gram. And then I'm going to find the decay constant of antimony 122. So first we need to find the mass of the sample because we have to do curies per gram, and we're given moles. So we're going to multiply by the molar mass of antimony, and now we've got our grams. Now we're going to use the activity in the mass to find the specific activity. We're given the disintegrations per minute. We got to convert minutes to seconds, so now we've got disintegrations per second. Convert disintegrations per second into curies. Here's our relationship. Then we're going to divide by total grams present. And here's our activity. Here's our specific activity in curies per gram. Now we're going to use the activity and the amount to find the decay constant. Your decay constant, K, is equal to your activity divided by the number of atoms present. Oh, that didn't turn out. Anyway, this is supposed to say 2.76 times 10 to the 8 atoms per minute divided by the number of moles times Avogadro's number, and we're going to get our decay constant. 1.8 times 10 to the minus 4 per minute. Well, that sucked. Oh well, it is what it is. I'm not doing this again. All right. Measuring radioactivity. There was a mistake in the overheads, that's all. We're just going to talk briefly about some instruments to measure radioactivity. Film badges use film because that's how radioactivity was first discovered. Becquerel had his photographic plates with film, and they would get fogged up by radioactive substances. And so film's been used to detect radioactivity ever since. And so film badges are used, are worn on they're clipped to your clothes, or you wear one on your ring, on your finger ring, to measure their own exposure. Another thing you can do is use a Geiger counter. It's got this little amplifier and counter box, and it's going to be attached to a tube that will pick up radiation, and if it detects radiation, you will get clicks. It will make an audible click when it detects radiation. Fun fact about Geiger counters is you can hold them up to your throat and you will get clicks. Because potassium has an isotope that occurs naturally and it's radioactive, and so if you eat your bananas or something else with potassium, it will collect in your thyroid, so you will get clicks from your throat because your thyroid's in your throat. So, fun fact. Yay. Okay, another way we can detect radioactivity is called phosphors. Some substances, when they absorb radioactivity, they'll emit light. And we can use this property and stick this stuff into an instrument called a scintillation counter to count instances of decay, because these instances of decay will be turned into light, and that's pretty easy to measure. Okay, those are phosphors. Okay, and now we're going to use our kinetic skills from 2 chapters ago, kinetics, to discuss radioactive decay, because we saw that from our decay equation a couple slides ago, radioactive decay is a first order process. So we can use our first order integrated rate equation to describe radioactive decay. The natural log of the ratio of our sample at time t versus our sample of time 0 is equal to negative kT. And now we can do some calculations using our integrated rate equation regarding, and now we can apply it to something new, radioactive decay. So let's do that. We have a sample of strontium-90, and let's say it has this activity, 1.2 times 10 to the 12 disintegrations per second. What's the activity after 59 years have gone by? So there's our value for T. Here's our half-life for strontium-90, 29 years. So what we're going to do, we're going to calculate K from our T1/2 that we're given, and then plug that K into our integrated rate equation. And here's our activity at time 0. What's our new activity after 59 years? Remember, always make sure your answer makes sense. More than one half-life has gone by, so less than half will have decay. More than half will have decayed, less than half will be left. Okay? All right, so here's our solution. First, we need to calculate K. Here, T1/2 is equal to the natural log of 2 divided by K. So, K is equal to natural log of 2 over T1/2. So here's natural log of 2. We're going to divide by 29 years, and here's our K in units of per year. Now here's our integrated rate equation. So we're going to plug in our numbers. Here's our K we just figured out. Here's our time that has passed that was given in the problem. Here's our initial disintegrations per second given to us in the problem. So we just do the math, and here we are. Natural log of our sample at time t is 26.4. Do your inverse log of both sides. So your activity at time t is 2.9 times 10 to the 11 disintegrations per second. How much has decayed? The fraction that has decayed, well, our amount at time 0 minus our amount at time t, divided by amount at time 0, plug in our numbers, 0.76 has decayed away. So more than half is decayed away, which is what we expected, because more than one half-life has gone by. 59 years has gone by. Always make sure your answer makes sense. All right, so this is where we stopped. So I'm going to stop this lecture for now, and we'll keep going on Thursday. If you have any questions about this lecture, go ahead and email me, or if you like, you can also type in a comment below the video on the YouTube website. Thank you for listening.